Now, Nicola Corbellini and
Alessandro and
Gabriele, they will give you a short session about the motion capital and how to work.
Yeah, exactly. Everything depends on how much time you want to spend on this, because we could have a lot of materials, starting from a theoretical overview, since we know there are some students from the human-computer interaction which are new to the topic, I think, but many of you should not be new. So maybe I will go fast on this theoretical and boring part, took the hype before we come to the practical work. But anyway, let's make this curiosity driven. So as soon if you have a question or you want to stress some topic, just please interrupt me and let's focus on that. Just like that. 1 hour. I think it's fine. Okay. Okay. Yeah. Okay. So basically, the theoretical part is mostly to let you know, since I'm very precise and picky on the terminology, that motion capture is an umbrella term. It's not just this technology, but I've seen in previous talks that you've already managed to do something with motion capture with accelerometers, or yesterday you were presenting something with a gesture interface. So that is motion capture too, basically. And in fact, motion capture is the process of recording the movement and translating it into 3D trajectories or 2D trajectories, actually. It has a lot of application domains, from biomechanics and sports, for entertainment in general, so movie, webpacks, video games, robotics and AI to record the data sets and train the models, and media and art and XR, in fact, like you are interested in, I think. There are mainly 3 paradigms, which is the marker-based technology, which is exactly this one. It's an optical technology. They emit infrared. The infrared is reflected against a reflective material, which is the marker. It is very accurate. It can reach sub-millimeter accuracy, and it is very precise also in speed, in time, because you can have up to, at least with this system, you can have up to 500 measurements each second. But accuracy comes with some cons, so the portability of the system is basically 0, and you can set up this in a controlled environment, in a controlled lab environment. There is another paradigm, which is the one of IMU suites. Don't know if you have ever encountered these. Basically, they are wearable suites with IMUs, so accelerometers, like those you've experienced this morning. And they help to track motion, but you cannot have absolute position. So you do not have the precise location in space. And they have some cons, like they drift over time, but they are still very precise as a time resolution. They are wearable, so portable, and you do not need cameras like this. Another paradigm is the one of markerless. So maybe you could know MediaPipe, which is very famous, I think. And they are the most portable, not very precise, let's say, with many pros and cons. Some are only 2D, some are only single person, some are 3D, some are multi-person. And the FPS, so the rate of speed, the data sent, much depend on your hardware. What else? Let's focus on this technology. Here, as I said, the underneath technology is the time of flight. So each camera is an infrared emitter. It emits the infrared light, it bounces on the retroflective material, which is the marker, bounces back, and the camera tracks the time of flight the infrared light take to reach the marker and get back to the sensor, which is again the same camera. Each camera performs the processing on board, and they only track the 2D trajectories that they are merged together on the computer. Each camera is synchronized, and there is this, let's say, tool they allowed, which is to desynchronize cameras, since each camera is an infrared emitter and each other camera is an infrared sensor. They can basically produce a problem on each other. You can desynchronize the cameras such that only this group emits at a specific time, the other groups emits right after, so they don't read the emission each other if they belong to different groups. If it's not clear, I see faces that are, let's say, what have you said? So interrupt me and ask if you have problems. Maybe we can go faster on this part. So IMU-based motion capture is the one with the inertial measurement units, the accelerometers. It's portable, it has ecological validity, it can be used outdoor, it allows for long continuous recordings, but at the cost of positional drifts. You cannot record absolute positions, so you do not have precise millimeters position or meter positions, but you do not have the precise location in the position. And it has lower accuracy than optical systems like this one. Markerless, it has zero setup. It is scalable to crowd and multi-subject with open pose, for example, and it is extremely low cost. It has way less accuracy. It can hallucinate. For example, it detects also shadows as person because the silhouette is very similar to the body, so you can have false positives. And another important thing is that it cannot track rigid bodies, which actually is possible with this system in the sense that you cannot only strictly measure body pose, but if you put the markers on like a musical instrument, or for example on the corners of this table, and you move that in the space, you can even track the position, the motion of this of an object, which is not possible with the AI system. Otherwise, you should train on purpose for that specific object. One important concept is the one of the marker set. So where and how you position the markers on the body. There are different sets, different protocols. One very common which we use is the sport marker set. It has a minimum of 41 markers and some optional one. And it is, let's say, optimized for complex and high-speed movements because there are multiple markers close together to minimize the occlusions or the soft tissue skin artifacts, in the sense that if you place a marker on soft tissues, your tissue moves and the marker gives you an unreliable movement. So you should always place it close to the actual joint to minimize the fact that the marker is moved by your skin moving. There is, for example, another one, which is the VR marker set, which is mainly focused on head movements, of course, and hands. The rest of the body is not very important in VR. Or you can invent your own marker set that can be task-specific. And, for example, to measure the position of rigid bodies. Like here in the past, it has been done with the quartet of arcs, and you can position it on the, I don't know the name, but the stick you use to play the violin. So you know the position of the instrument, the tool. So, what is a recording pipeline? First thing is to position the cameras. You should cover at best the volume you are interested in recording. One of the advices that people from Qualisys gave us is that since each camera has a cone, you should focus to have that specific camera to cover the closest area. So if you can think about those cameras up there, they are pointing right beneath them instead of pointing to the other side of the stage. That's an heuristic advice they gave us. Then there is an important part, which is the calibration. So we will use those tools, which are markerized iron sticks. One is an L frame, But probably I will go deep. Yes, I'm anticipating too much. So there will be the vesting phase in which you position the markers. There will be the actual recording phase. Then there is a phase which is called generating an aim model. So you can regenerate a model of the body. So the system already recognizes the markers and applies names and bones between the markers. Then there is a cleaning and interpolation phase in which, of course, this auto-label with the aim is not 100% accurate. You have to manually clean and relabel where you lose maybe the joint, the track, there are occlusions. You can interpolate if there is some time in which a marker disappears, it is occluded. You can try to infer which were the position during that occlusion time, and then you can export your data. So, camera placement. Basically, a lot of dots to say cover the most volume you can and position them logically, reasonably. Calibration process. First thing is placing the L frame, which is the one I was mentioning before. It's this L tool which defines the origin of the digital space. So at the angle of the L frame, there will be the 0, 0, 0 point in your digital world. It will also define how the axes are placed. So your X horizontal axis, your Y vertical axis, and Z is the depth. And you can have some quality metrics, so the amount of error you have. Now, the cameras return the amount of error they do in trying to inferring the position of markers, and you can basically redo the calibration or stick with that calibration if the quality is fine. Everything will be more clear when we move to the practical part. Testing the subject, nothing. You choose a marker set, you stick the markers on the body. One thing I have not said, there are two kinds of markers. There are passive markers, the one we're going to use today. They are just reflective. There are active markers with a battery each, and they actively emit infrared light. They are used for very long distance recordings or to minimize occlusion. They are more reliable and trackable. Recording trials, usually you start, but that's not mandatory, in a static T pose. So people will stand like this, and then you perform the task. And you can even use an external sync. There is a specific synchronization unity that the quality system provides. And it serves to generate a timestamp that you can send to other devices, so you can have synchronized measurements among the quality system, accelerometers, the Kinect, and you can have for each timestamp the same recording at the same exact time. The aim model is used to apply labels to the markers, so you know that the shoulder is the shoulder, and that's it. Not very much to say. You will see how to generate one, but it's very easy. And export formats, there are plenty. It's FBX if you want to work with Unity, Blender, and Unreal Engine. A TSV is the one we use mostly. It's like a tabular data. Or C3D, which is a standard for MATLAB and Python, which actually I've never used personally. Takeaways is three paradigms: marker-based, IMUs, markerless. You can have passive and active markers. The architecture of the system, so cameras are all synchronized, but you can desynchronize a group of them so they don't interfere with each other. And that's it, that you have a marker set. I would say, let's do the calibration so you can actively see what our recording section works. Guys, if you're ready, place the L. Or is there any volunteer that would like, yeah, come. Gabri. She will do. She. go there and he will instruct you. So you have now they're mounting the L shape. This defines the origin of the space. So in the digital reconstruction of the world, it's not important at this moment in the sense that we can just, this is the x-axis. So the long axis is the x coordinate. And I admit that I not always remember in which direction, but from one side to the other is the positive axis, so it's the plus x. On the other side you have the negative axis, so it's minus x. Here we have the y-axis, is the height, and here we have the depth, so the z-axis, again, positive from here and negative from here to there. This is the magic wand. It has a precise measurement, so this is a length of 750.4 millimeters, because the system knows the exact length of this and it can calibrate, can make sense of how these markers are positioned and can exactly calibrate. I don't know how to explain that in other words. So now, usually calibration takes 60 seconds, but we can go with 90 maybe. Yes. You should. The idea of the calibration is walking back and forth, moving these. From policies, they suggested us to do that like this, and then sometimes you turn on the other direction. The idea is you want to paint the most volume you can inside the area covered of the cameras. Okay, you can start exactly from there, and you usually go back and forth, and you turn, you cover all this space.
Oh, I cover all this space. Okay.
Exactly, all these, imagine a rectangle and an ellipse.
And in front of that as well?
Yes, all this space that it has not to be very precise, now it's a demonstration. You can cover all the stage space in this direction, but also in height. So you have to, exactly.
Only this, like this movement, or does
Yeah,
it have-
I give you an example. You can do like that. Start from low, you go up. You can do like that. More slow, yes, but very fast. And you can also cover on this direction.
Oh, okay. I can go multiple times on the same.
Yes, exactly. So I don't know if you can read from here. Here you define a calibration time. And second, I cannot even read. Second, you define the rate the cameras are emitting. Second, at 100 Hertz. You say which wand you are using, so the camera knows this is the 750.4 wand, and nothing. It will emit a sound as soon as it's finished. So are you ready? 3, 2, 1, go. 19 seconds is an eternity.
Okay.
And you're almost done. You can see the results here. So calibration passed, very good. You never explore the interface, so maybe you can do that. Can you read the basic from? No? Okay. I don't know how to solve this. But basically, you have the calculation result. The cameras, which are 19, and there are basically average residual in millimeter. So the average error in millimeter each camera does in trying to detect this magic wand. So it's, I don't know, more or less, okay. Yeah, average, total average is almost 1 millimeter, which is very precise, but can be made lower. And okay. Okay, we just take a look at the interface. Here there is the size of each camera. Each camera is numbered. You can see the name, you can barely see the dot moving. This is the magic wand that is moving. And exactly, this is so. This is the wall side volume covered by the side of the cameras. And can you activate the other one? This is the calibrated volume. So the volume you painted, as you can see, it could be made way bigger, but of course we cannot reach a very impressive height. So this is the wall volume covered, seen by the cameras, and the calibrated one. Then, can you switch back to the cameras? Here is what each camera sees. They are numbered. We have, I don't remember how many, 13 infrared cameras and 3 RGB cameras, which are at the corners of the stage and close to the laptop, which is on the ground. What else? Here you can define the capture rate. We are going with 100 Hz, so we have 100 samples of positions at each second. It can reach up to 500 Hz, which now is red because we have desynchronized the cameras, in the sense that they are put into groups. So I don't know if you can make this scene in the sense exposure group. It's difficult to, yeah. So camera 1 belongs to the camera group 1. We have 4 groups, 5. And camera, I don't know which, camera 11, which I don't know where it is positioned, it belongs to group. So they are, each camera in this group is desynchronized with the other groups. Also, to prevent interference, you can even apply manually some masks. So you can place a mask like this under this green rectangle. There would be a white dot like this, which I imagine you cannot see from there. But they are like it's interference from the light, for example, or some iron, like for example, yeah, here there is nothing, there is the enemy one, nothing. And yeah, so basically you can just place manually a mask, so you say at the camera, don't calculate what's there, because I know that there will be something reflected which is not a marker, and I don't want to position. And you can also change some other parameters like the exposure, the marker threshold, or what else. You can have a video. Can you go to video, please? You have the video side of each individual camera, so this is useful, of course, for positioning them to see where they are pointing, and that's it. So we have calibrated the system. Now it will be the time to record the data. In the interest of time, we will not be placing the suite on someone because it takes a lot. If you want, you can wear that wristband, which has 3 markers. That, what? Yeah.
I see there's a lot of reflection from the floor.
Yes.
Does that interfere with the camera or the sensors?
Yes, it can, they can detect it. In fact, that's the reason why you place manually masks. If it's not a region that you are interested in measuring. Otherwise, I don't know, you should control the lights of the environment.
The perfect set will be with the non-reflective floor, right?
Yeah, definitely. Yes, we could even turn off the lights since it's infrared, they don't need light. And yes, they are infrared, so yeah. So we can remove the wand and the L, and can you go read me, please? Can you see yourself? This is what we see like at this rest condition, but Policies as a real-time protocol to streamline the data in two conditions, which is one which the Policy, the QTM in the software, it emits whatever it records at its own pace, and it's up to the server receiving to keep up with the speed. Otherwise, you can pull, so it's the laptop asking at his own pace when receiving a new frame of data. So maybe we can try to record one session to generate a name model, so you know and see what it is. And then we can also try to open Touch Designer and see real-time data sent. But that's just for demonstration purposes, because what only changes is the rendering, because you will see again 3 spheres moving in the geometry space. Let's do a recording session maybe. Yeah. Here you define yeah, the folder where to save the data. Okay, it's fine. Okay. New folder.
So I have one more question.
Yeah, sure.
Where are all these cameras plugged in? Like a video matrix?
They are plugged in. Yeah, actually, good question. I forgot to say that. Each camera is plugged into a battery management. I don't know how to call that. A battery unit. Each battery unit has this logic. It can handle 10 units, in which a camera like this costs 2 units. An RGB camera costs 1 unit. So you can connect 5 of these or make a combination. So you just link them. Yes, they are linked with these Ethernet cables that they serve both as power and to send the data. And they are bridged one another into groups.
Up to 10 units.
Up to 10 units, yes. So, and each of these is 2 units, so up to 5 maximum.
And how many can you link?
How many can you?
How many cameras can you bring? What's the optimal setup or the maximum?
I don't know about the maximum optimal setup. I think it should be around 8, 10, and we have way more than that.
4 times more.
No, we have 16 in total, so twice. And yes, that's it. They are linked in a chain, and we have, I don't remember, 4 chains. Four chains probably, yes. So 4 power batteries of 10 units each.
And there's a synchronization unit there.
And there is the synchronization unit which is served to synchronize the camera or desynchronize them together. And yeah, that's it. So yes, go with the recording trial.
When you're ready.
And I'm just looking
That's whatever you want.
Thank you.
Yeah, just move a little. Yeah. I think it's 5. Yeah. Okay. Here we have the process data. Here are the trajectories detected in a field level, in the sense that this marker has been seen 100% of the time. There are multiple trajectories because the camera detected also some noise. And since this is seen 100% of the time, we can reliably say that these 3 trajectories are the 3 markers, and the remaining ones is noise. So you can maybe move the trajectories in the labeled one, you can apply a labeling, what you say.
I'm looking at the because the trajectories are just the reflexes.
Yeah, interferences, the reflexes that we mentioned before, they have been located here.
Here.
For example, exactly there is something which I don't know what it is. Trajectory is the sequence of positions across time. It's X, Y, Z of the markers during the time. The first 3 that are 100% filled are the 3 markers of the wrist. The remaining one is noise, like lights on the reflections of the ground, or probably these lights, or whatever. Here you can see the trajectory, in fact, at each time stamp, so at the frame time number 350, there are the X, Y, and Z. If any occlusion occurred, you would have a gap here, and you could apply an interpolation, so mathematically filling the missing values with, I don't know, there are different techniques like spline, you can just place the average, or many other techniques. So, here trajectories are unidentified, they are named as unidentified. You can bring them here in labeled trajectories. You give a name, so wrist in, for example, wrist out, and something else, wrist into, okay. Now they are colored, and at this point we have bones, At this point, we could create a name, so we instruct UTM to say every time we see markers with this configuration, automatically label them with these names. So you can have the skeleton automatically labeled with shoulder, elbow, wrist, so on and so forth for the product features. We are creating a new model. Can you zoom on? We enter the name of the model. A wrist AIM. AIM stands for Anatomical Intelligence Model. And that's it. So we created the AIM with just one recording, but you could apply further any other recording to refine the model so it can more reliably understand, more reliably automatically label the trajectories with the names. Okay. At this point, we can maybe stream the data.
And while we record, we stream the data.
Yeah, okay. We can do another recording session if you're fine. In the meantime, we set up the other machine. In that laptop, there is a Python server that listens to QTM, receives the positions, and sends the position to Touch Designer. So it is served as a bridge. It receives and sends in localhost to Touch Designer that is installed there. We prepared a very basic patch in which there are 3 spheres instantiated at those positions, and you can see basically the exact same thing done in Touch Designer. When you're there, what's the problem?
The names are
The names are different from those I used as a test.
here.
So what kind of data does it send to that?
X, Y, and Z position.
So
Yes.
a saw.
What?
A saw.
Yes, we are using POPs.
Yeah.
The new ones, point operate, the blue ones.
Yeah.
But you can use SOPs also. And then you can do whatever. Then it's basically the rendering part. You can invent whatever. For example, if we have time, I can show you ISWeb, which is our library in Python. We created a plugin in Touch Designer, so you can know. Yes, we have the data, and then what do we do? We have some, I don't know if you know the features that are movement features that we compute here. So for example, you could provide X, Y, and Z to these TOX components that we have, and compute how smooth your movement is. You can compute the geometric symmetry, if you are symmetric over an axis or not symmetric, stuff like that.
So you can send the full body link.
Yes. Yes, and if you have the markers of all the body, it is sent, and then whatever you do there is up to your fantasy, creativity, and stuff. Are you ready?
No,
More or less.
perché avevamo 2 domande.
So what's the problem?
Perché non so se mai no.
So the IP of the sending machine has changed probably during the boot, so we will change that in the code and it should work. So later I can show you what PyISWeb is, the Python library, the documentation, the Touch Designer plugin, and I can show you how to install that. And there are some example patches that you can navigate to learn that as a tutorial, and then you can, I don't know, use it if you need it. So that you can see what I'm doing. Okay, so now it has become a live session. This is the OSC receiver. You can see the positions as soon as you move. And the problem is that we tested that with a name made of two markers, named like marker 1 and marker 2. Now they've changed the aim, and touch designer expects different labels basically. So we can just change the naming and instantiate one more sphere, and then we will have the marker. Okay, our sphere is done. Can you make it bigger? Okay, sorry for the waiting. We are done. Can you increase the sphere? Uniform scale. Yes. So we are just reading. We are just reading two of the three markers, and that's it. We have the data in Touch Designer, and at this point we can do whatever we want. Maybe if we can show the smoothness. We are increasing the speed. No, the speed of the loop. And then we keep the speed in input, the blocks to increase the smoothness, because that's the rate of the acceleration. So basically we go from speed to position, speed. From speed we complete the acceleration, completing the gradient, and then the gradient again to complete the jerk, which is the variation of acceleration in time. And this tells us how much smooth or jerky, like a vibrating start trouncing, you are. It can barely read, but that one should be. If you start making very different speed and acceleration, the values increases, and as it goes higher, it means that you are not smooth. Yes, the jerk one, so the yellow one. Okay, so this is an example, and for the so far everything clear. You have questions, doubts? Okay. We can navigate by IceWeb, and then I will show you the example patches in Dutch Designer, unless you tell me that you are interested in Python. We have notebooks, but that's very much programming, very low level. I don't know how much you're interested, what you prefer. See. So, IceWeb. There is a long tradition here in lab of analyzing movement. And years ago, they developed a conceptual framework to conceptualize, in fact, you can come and see it if you want, sorry. I left you there. Yeah. Yes. Thank you very much.
Thank you.
So we are developing this library, which is called PyIceberg. It's not a brand new library in the sense we are inheriting works that has been done during in past years here in the lab in analyzing movement. I don't know if any of you knows IceWeb. Okay, it was a proprietary software here, open software. Let's say it was an ante-literal touch designer without the 3D rendering capabilities. It had a lot of sensor integration modules. It was a node programming environment, much like a touch designer. And there were modules to analyze movement that now we are porting into Python to modernize the system. Because maintaining a software like IceWeb is a lot of work, and we decided to move into a Python library. You can find it in GitHub. It's an open source tool, so if you are into Python development, you are interested, you could even fork and contribute. And above all, you could come and give a star. We a lot appreciate stars here, so please come and give us your star. I'm going to show you the documentation. So it's an expressive gesture library, inheriting from the IceWeb software. It's used in research, interactive media, health and rehabilitation, and artistic performances. And a little bit of theory again, sorry. But here in the lab, they developed in the past this conceptual framework in which movement is analyzed into layers, where they go from low level to high level. One important dimension is time. So at the lowest level, you have frame by frame data as soon as they arrive from the sensor. Otherwise, at the highest level, you have movement features that take some seconds to happen. So, for example, the kinetic energy of movement, you can compute that frame by frame. Otherwise, to say if a movement is, I don't know, sudden, you need a little history of time. So you need a buffer of some seconds. Another important discrimination is at the lowest level, we have physical signals, and as soon as we move up, we go into higher abstraction. And we move from the objective layer, so kinetic energy is physically objective, it's a measurement that everybody agrees on. At the highest level, there is a lot of cultural and subjective interpretation. So to say if a movement is light, it depends. It can be light for me, it can be less light for you. It depends on your culture, on your expertise on movement. It's subjective. So I'm showing you this conceptual model because the library is structured in this exact way. We have sub-packages. You can navigate. We have no physical signals for the moment because integrating sensors is a lot of work, and the API and SDK changes a lot, so it's a lot of maintaining stuff. I can give you an example of low-level features. It's the kinetic energy I mentioned, the postural contraction, so how much you are expanded or contracted, how much smooth you are, the equilibrium, so if your body center is between your feet, or otherwise it's going outside, the weight is going outside your stance. We have mid-level features, for example, the lightness of movement, the impulsivity, the fluidity and fragility. Not all these modules have been ported yet. And we have high-level features, which are very high level constructs, for example, the hesitation, the saliency or the emotion that is conveyed with the intention that the moving user, participant, is trying to communicate to the people. So here is the Python technical documentation. You have you can have both the theoretical part, a very high level theoretical explanation of what is being computed. For example, here we have the bounding box to see, we compute the box around the body, the area of the covered by the body, and we do the ratio of the two to see if you are covering a very high area, or if you are instead contracted. And we have an index that you can later use into Touch Designer, for example, to drive visuals, to drive sound, to do whatever. Here we have the API, not the data models, but the low level. The API documentation, so how to use that in Python. And for the Python part, it's basically this. Here there is the GitHub repository. And unless you want to dive into Python, I can show you how to install the Touch Designer version. That is, there should be a link somewhere, Touch Designer plugin. Yes, it's another repository called PyIsotd. It's a set of toxes. So I don't know how much you know Touch Designer, but they are modules you can drag and drop into your network. And here on the right, the releases, you can download the latest version. So I will show you maybe the example patches. Sorry, there is not a very good network. Is there a break contemplated of some coffee break? Is that after this, do we want to do that now? What? Dictate the time. Tell me what.
You are absolutely on time.
Okay.
We're not going on coffee break. We are just changing the activity. We are right now making the groups because we have to leave like, I don't know. Can't remember it.
Eles estão dele lá a fazer a análise.
Because I always have problems with the timetable.
Canta.
We have to leave at 4:30. So we have like 45 minutes to make the groups, to meet each other. We explain you what are we going to do, what you going to see here. So yeah, so
Okay.
we will not have a coffee break in somebody. Just whatever we now. You will be here tomorrow.
I will be here. Yes, of
Help
course.
people install.
Absolutely. Yeah.
Yeah.
Okay. If anybody has a questions, you can find me here the whole week. So, Nicola.
Okay. Great.